Okay, let's unpack this. Imagine you're in a car, perhaps cruising down the highway, or maybe it's one of those cutting-edge autonomous vehicles navigating a busy intersection. We place an incredible, almost unconscious level of trust in that machine, don't we? We expect its brakes to work, its engine to respond, its complex software systems to make precise, safe decisions every single time. But what if there's a tiny glitch? I mean, a single line of faulty code in a critical system isn't just an inconvenience. It could quite literally be catastrophic. For systems where lives are on the line, good enough simply isn't an option. It just won't cut it. Today, we're embarking on a deep dive into an extraordinary collection of documents, the NVIDIA SPARK Process documentation. Now, this isn't just a manual, it's a meticulously engineered blueprint for creating software with the absolute highest levels of integrity and safety. Our mission is to navigate this highly technical material, extracting not just what it says, but really why it matters. We want to transform what might seem like dense procedural jargon into compelling insights about how cutting-edge software is built to be incredibly safe, reliable, and maybe most importantly, provably correct. This is about understanding the hidden layers of assurance beneath the surface of our most trusted technologies.
Yeah, and what's truly fascinating here is that this documentation reaches far beyond just, the act of writing code. It presents a holistic, almost philosophical approach to safety assurance. At its core, it's about meticulously binding a specific, powerful programming language, Ada Spark, with the stringent requirements of ISO 26262. And for maybe not deep in this world, ISO 26262 is the globally recognized functional safety standard specifically designed for electrical and electronic systems within road vehicles.
Right, the big one for automotive?
Exactly. It's a standard that demands a level of rigor and proof that just transcends traditional software development.
Yeah.
So this documentation isn't just a set of guidelines, it's really a foundational framework for engineering trust from the ground up. And that trust isn't only for the end users who rely on these systems with their lives, but equally for regulators, auditors, and of course the dedicated engineers tasked with building them. It's a detailed blueprint, covering everything from the precise definition of specific terminology to exhaustive verification checklists and incredibly granular instructions on tool usage, all meticulously designed for nothing less than absolute precision and unwavering reliability in a domain where failure carries an unimaginable cost.
So let's begin by really digging into the fundamental what of it all, the NVIDIA SPARK process. It isn't a single magical tool or, a simple checklist. It's a comprehensive, structured software development methodology. When we talk about the documentation as our source material today, we're actually looking at a small but incredibly dense collection of related documents. Primarily, there's the core NVIDIA SPARK process document itself, which meticulously lays out the entire methodology from start to finish. Pretty detailed stuff. And then there's a crucial companion, a common document, which provides essential supporting information, things like licenses, and a detailed bibliography giving context to the framework.
That's right. And the overarching and incredibly specific objective of this entire process is vital. It's about leveraging the Ada Spark programming language to rigorously meet, perhaps more importantly, demonstrably prove compliance with, the ISO 26262 standard.
Okay, so why is this particular combination so profoundly significant? You often talk about the inherent strengths of certain languages. What makes Ada Spark, coupled with a standard like ISO 26262, such a powerhouse for these safety-critical systems?
That's a key distinction, and it goes right to the heart of building trust. Ada, as a programming language, was designed from its very inception with reliability and safety in mind. That was its goal. It has robust features like strong typing, which catches errors at compile time, not runtime explicit concurrency control, exception handling, features that inherently reduce common programming errors that plague other languages.
Right, the stuff that keeps developers up at night.
Exactly. And Spark takes this a massive step further. It's a formally verifiable subset of Ada, think of it as Ada, but with an added layer of mathematical precision. It allows you to prove with absolute certainty that certain types of errors simply cannot occur in your code.
It cannot occur. Not just unlikely, but mathematically impossible.
For specific classes of errors, yes. That's where formal methods come into play, using mathematical techniques to verify software properties. It's powerful stuff. Now, couple that with ISO 62622, like you said, it's the big one. It's not just a set of best practices, it's a rigorously defined functional safety standard specifically for electrical and electronic systems in road vehicles. Its primary purpose is to ensure the safety of these incredibly complex systems, and critically, to systematically mitigate any unacceptable risks that could lead to harm.
Things like unintended acceleration, braking failures, the nightmare scenarios.
Precisely. Every single line of code, every design decision, every interaction within that system needs to be demonstrably safe and reliable under all specified conditions, and also gracefully handle unexpected ones. So a deeply rigorous process like the NVIDIA SPARK process becomes absolutely necessary to achieve this level of proof. It moves beyond traditional testing, which remember can only ever show the presence of errors, never guarantee their absence.
Right, you can test forever and still miss something.
Exactly. This process moves towards methods, including formal verification, that can mathematically prove the absence of certain critical errors. The very foreword and purpose of this document within the NVIDIA SPARK Process documentation emphasize this. They make it crystal clear. This isn't merely a helpful guide or a collection of suggestions. It's presented as a prescriptive standard for building safety-critical systems, a foundational blueprint that leaves very little to chance.
And you mentioned there's even a section on how to read this document.
Yeah, which tells you something important right there. It hints at its inherent complexity and the methodical, almost scholastic engagement required to truly grasp and implement its principles. It's definitely not for casual browsing. It's for engineers and teams committed to building the safest software possible, where every word and every process step is weighed for its impact on ultimate system safety.
And it's not just about internal process either. I noticed the documentation mentions the GNU free documentation license, version 1.3, for the NVIDIA SPARK process document itself. That seems, well, quite interesting for something potentially so proprietary, doesn't it? What does that licensing imply about the documentation's accessibility, or maybe its broader intent within the safety-critical software community?
That's a really perceptive observation, actually, and it speaks volumes about the document's broader purpose. The choice of the GNU Free Documentation License, or GFDL, for such a critical methodology suggests a significant degree of transparency and, I think, a potential desire to contribute to the wider safety-critical software ecosystem.
So not just keeping the secret sauce to themselves.
Exactly. Unlike proprietary internal know-how that's kept under lock and key, licensing it under GFDL means it's intended to be copied, studied, modified, and redistributed, usually with the caveat that modifications must also remain under the same license, maintaining that openness. This isn't common for highly specialized, deeply integrated industry processes. It implies that NVIDIA might see this not just as, say, a competitive advantage, but as a framework that could potentially benefit the entire industry, fostering a more rigorous and maybe even collaborative approach to safety.
Especially in areas like autonomous driving, where public trust is everything.
Absolutely. Where public trust and universal safety are paramount, sharing best practices and verifiable methodologies can actually accelerate overall industry progress rather than hindering it. It suggests a commitment to advancing the state-of-the-art in safety-critical software beyond just their own internal projects. It's an unusual, but I think a very welcome signal of openness in a domain often characterized by proprietary secrets.
Okay, here's where it gets really interesting and quite illuminating about the mindset required for this work. When you delve into the NVIDIA SPARK process documentation, one of the first things you encounter right after the general overview is this comprehensive terminology section. It spans from term 4.1 all the way to 4.33.
33 defined terms.
Yeah, 33 incredibly specific terms, each with a very, very precise meaning. The sheer number and the granular nature of these defined terms immediately tells you about the almost microscopic level of precision demanded in this domain. It's like learning an entirely new language, isn't it? A highly specialized dialect, custom-built for software safety. You can't just casually use terms here. Every single word is chosen for its exact meaning to eliminate any ambiguity, which is, of course, absolutely crucial when human lives are potentially on the line. Can you help us unpack a few of these critical terms? What do they truly signify in the context of building provably safe software?
Absolutely. And you're right, this precise vocabulary isn't just a formality. It's the very bedrock upon which all subsequent assertions of safety are built. Without this shared, unambiguous understanding of terms, communication errors could easily creep in, undermining the entire safety argument. Let's unravel some of the most compelling ones. First, consider software unit, or unit, and its vital distinction from unit-level work product versus non-unit level work product. This immediately clues us into the granular focus of this methodology. A software unit is defined as the smallest, independently verifiable component of the software.
Like a single Lego brick.
Exactly like a single, perfectly crafted Lego brick in a massive, complex structure. A unit-level work product then refers to any artifact directly related to that single, isolated unit. Maybe its detailed design document, its specific test plan, or the code itself. In contrast, a non-unit level work product will be broader encompassing things like the overall system architecture, the integration plan for multiple units, or global safety requirements. This atomization of software into small, manageable, and highly verifiable pieces is absolutely critical for safety. Why? Because it allows for exhaustive testing and rigorous formal verification of each component in isolation. It makes it far easier to pinpoint and prove correctness, and then systematically build up that assurance for the larger interconnected system. It ensures that no single brick is inherently flawed before it becomes part of the wall.
Okay, that makes sense. Then we see terms like Spark Platinum, Clean Spark, and Clean Spark Platinum. Sounds impressive, but what do they actually mean?
Right? They aren't just fancy names or marketing buzzwords. They denote very specific ascending levels of rigor and assurance applied to the code. Clean Spark implies that the code has undergone a preliminary but rigorous set of checks, adhering to a very strict subset of the ADA language. This cleanliness makes the code suitable for formal verification.
So clean means provable, essentially.
In a way, yes. It means it's structured in such a way that mathematical proofs about its behavior can be generated much more easily. Platinum then signifies the absolute highest level of assurance achieved, typically through extensive application of those formal verification methods, actually doing the proofs. And this leads directly to a crucial strategic concept mentioned in the docs: cleanliness-adjusted ASIL.
ASIL being the automotive safety integrity level.
Exactly. ASIL D being the highest, implying extreme risk if it fails. But here, the cleanliness of the code, how rigorously and formally it has been verified, can actually influence how its safety integrity level is assessed.
Wait, so proving your code is super clean can affect its safety rating?
Potentially, yes. Cleaner, formally verified code isn't just about technical purity, it's a profound strategic advantage. By mathematically proving code correctness to such a high degree, teams can often streamline later-stage testing, accelerate certification processes, and potentially even reduce the overall cost of compliance. Imagine the confidence a regulator or, say, an insurance company has when you can demonstrate with mathematical certainty the absence of critical errors, not just their presence after months of testing.
That's huge.
It is. This cleanliness-adjusted ASIL is where engineering rigor directly translates into tangible business value and unparalleled safety assurance. It signifies a shift from simply testing in quality to actively building in quality and proving it.
All right. What about the distinction between formal versus non-formal unit requirement design constraint and formally verified versus non-formally verified? Sounds related.
Very related and absolutely paramount. To put it simply, imagine a non-formal requirement. The car must stop safely. Sounds good, right? But what does safely really mean? How quickly? In what specific conditions? What even constitutes a stop? It's ambiguous.
Open to interpretation, which is dangerous.
Precisely. A formal requirement, however, would be expressed in a precise, unambiguous, often mathematical or logical notation. Something like, brake pressure must reach 90% of maximum within 100 milliseconds of pedal depression, under all conditions up to 100 kilometers, and maintain deceleration of at least 7 meters per second squared.
Okay, much clearer. No wiggle room there.
Exactly. This kind of precision leaves no room for misinterpretation, and is crucial because it allows for mathematical analysis and proof. Similarly, formally verified means that the code has been mathematically proven to satisfy its specifications, often using tools like the Geniet Proof tool we'll discuss later. This offers a much stronger guarantee of correctness than traditional non-formally verified methods, which typically rely heavily on testing. Remember, testing shows presence of bugs. Formal verification can demonstrate their absence for certain properties. That provides a level of confidence essential for the highest safety levels, like ASIL D.
Got it. And how about out-of-context comprehensible versus in-context comprehensible? What's the idea there?
This refers to how documentation and code should be understood. Out-of-context comprehensible means a document or a specific code segment can be understood entirely on its own, without needing to refer constantly to other parts of the system or external documents.
Like a well-commented function that explains itself.
Exactly. It clearly explains its inputs, outputs, purpose, maybe its limitations. In-context comprehensible, on the other hand, means it makes sense when viewed as part of the larger system, understanding its specific role and interactions within the complete architecture. This dual requirement speaks directly to maintainability, reviewability, and long-term safety. If a new developer or a safety assessor needs to understand a component, they should be able to grasp its function and properties both in isolation and how it fits into the bigger picture. It significantly reduces the chances of errors due to misunderstandings, incomplete information, or just a fragmented view of the software. It's about ensuring clarity at both the micro and macro levels.
And then there's the human element, local peer review versus global peer review. Why the distinction?
This highlights the vital human element of quality assurance. Even with the most sophisticated automated tools, human oversight and diverse perspectives are indispensable. Peer review is a critical mechanism for catching errors, identifying overlooked edge cases, and ensuring adherence to standards. Local peer review typically involves a colleague reviewing an individual's specific work product, like a single unit of code, its detailed design, or maybe a test case. It's focused on the fine-grained details.
Looking closely at one piece.
Right. Global peer review, however, would be a broader, higher-level review of the entire project's architecture, the overall safety case, or the project's compliance strategy. This might involve senior architects or safety managers reviewing how all the units integrate or how the entire system meets its ASIL targets. These human checks are incredibly vital alongside automated tools. They provide different perspectives, catch errors that tools might miss, like subtle logical flaws, and ensure holistic quality and alignment with the overall safety goals. They act as crucial human safety nets.
Okay, and finally, the docs list a bunch of specific file types like GPR, ADC, ADS, ADB, and so on. Are these just file extensions, or is there more to it?
Oh, there's much more to it. They illustrate the incredibly specific tooling and structured file organization that are inherent in robust NVIDIA SPARK development. These aren't just arbitrary file extensions. For instance, a GPR file is a GNAT project file. Think of it like the conductor of an orchestra. It defines the entire project structure, build parameters, compiler switches, dependencies for the GNAT toolchain.
So it tells the tools how to build everything.
Precisely. An ADS file typically refers to an ADA specification file. This defines the public interface or the contract for a software unit specifying what it does without revealing how. It lists procedures, functions, types, constants that others can use. An ADB file is the ADA body file, which contains the actual implementation details, the how of that unit. The concept of external ADS file and internal ADS file relates to whether a unit specification is defined within the current project or imported from, say, an external library, which is crucial for managing dependencies properly. And an ADC file is an ADA context file, often used for specifying configuration information or specific compiler settings, pragmas, that apply to a particular compilation unit. These specific file types aren't just about organization. They enforce modularity, promote separation of concerns, interface versus implementation, and fundamentally support the powerful compilation, linking, and formal analysis features inherent in the NVIDIA SPARK ecosystem. They are an integral part of making the code provable and maintainable.
That level of detail for just the terminology, wow. It truly drives home how foundational precision is in this entire process. It's not just words. It's a language crafted for undeniable clarity. But it makes me wonder, does such a granular approach, almost creating a new language, ever risk slowing down development or making it harder for new engineers to get up to speed? Or does the long-term safety benefit just massively outweigh that initial learning curve?
That's a very perceptive question, and it's a valid concern in any highly specialized domain. Initially, yes, there's absolutely an upfront investment. For new engineers or even experienced ones coming from less rigorous environments, there's definitely a steeper learning curve. They need to internalize not just the NVIDIA SPARK language itself, but this very specific, precise vocabulary and the associated mental models. It's a bit like learning to speak the language of a highly specialized craft, like, say, watchmaking or aerospace engineering.
Takes time and effort.
It does. However, the consensus in the safety-critical domain is that the long-term benefits overwhelmingly outweigh that initial investment. Why? Well, first, reduced ambiguity. Misunderstandings, which are a huge source of errors and costly rework in software, are dramatically reduced. Everyone is literally speaking the same language with the same definitions. Second, increased predictability. The behavior of the software becomes far more predictable, not just during normal operation, but also under fault conditions, which is obviously crucial for safety. Third, enhanced maintainability. Future changes become safer and easier because the code and documentation are unambiguous and formally structured. It's actually easier for a new team member to understand a system built on these principles, even if they have to learn the language first, compared to trying to decipher an ambiguous, poorly defined system years later.
Right, the long-term payoff.
Exactly. And perhaps most significantly, accelerated certification. This precision directly translates into an accelerated and smoother certification process with regulatory bodies like the FAA or automotive safety agencies. When every term, every process step, every tool configuration is meticulously defined and traceable, it dramatically simplifies the auditor's job. They can easily verify compliance because the blueprint is so clear.
Makes sense. They can just follow the map.
Precisely. So while there's an initial push to climb that learning curve, the dividend is a system that is not only safer, but also ultimately more efficient to develop, verify, and maintain over its long operational lifetime. It's an investment in robust engineering that pays off in reduced recalls, fewer failures, and ultimately greater public trust.
That's a compelling case for the investment, definitely. Having understood this specialized language, we move to what feels like the bedrock of the entire methodology, the prerequisites and assumptions section of the NVIDIA SPARK Process documentation. So what does this all mean for someone wanting to implement this in their own development cycle? It tells us quite plainly that you can't just jump in and expect this process to work effectively.
Right. Absolutely not.
There are fundamental conditions, underlying truths, and specific beliefs that must be in place for the process to function as intended and to actually deliver those crucial safety assurances. It's essentially about setting the stage correctly, meticulously preparing the ground before the real work of designing and coding even begins. What are some of these critical foundational elements, and what are their practical implications for a development team?
Exactly. And these aren't just, boilerplate formalities you skim over. They are incredibly practical implications that fundamentally dictate the environment, the capabilities of the team, and the foundational understanding required for this process to succeed. If these prerequisites aren't met, the entire safety case built upon the Spark process could be undermined. Seriously. Let's start with the general assumptions. These are the foundational truths or overarching conditions this process relies upon. For instance, it assumes adherence to standard, sound software development practices, meaning things like using version control, conducting code reviews, and having basic project management are already in place and well understood. These are table stakes.
Just good engineering practice, basically.
Right. It assumes the presence of competent and capable development teams, individuals who possess the necessary skills in software engineering, and more specifically in Spark, or are willing to be trained. Critically, it assumes an organizational culture that fundamentally prioritizes safety throughout the entire development lifecycle, viewing it not as an add-on, but as an intrinsic value.
So management has to be fully bought in.
Completely. This means leadership buy-in, adequate resource allocation, and a commitment to quality that permeates every decision.
Yeah.
Without this foundational commitment, even the most detailed process will inevitably falter. Then, a paramount prerequisite is consistent ASIL. We've discussed ASIL, the Automotive Safety Integrity Level. It's a key metric from ISO 26262, classifying the risk of a system's failure. Maintaining absolute consistency in this ASIL across the entire project is non-negotiable for safety. Think of it like a chain. Its strength is determined by its weakest link.
So you can't have an ASIL-D system with one ASIL-B component dragging it down.
Precisely. If one critical component of an ASIL-D system, the highest integrity level, is inadvertently designed or verified only to an ASIL-B standard, that inconsistency introduces an unacceptable risk into the entire system. The NVIDIA SPARK process demands that the ASIL is rigorously and uniformly applied from the very first conceptual requirements through detailed design, meticulous implementation, and exhaustive verification. This consistency impacts everything. The choice of development tools, the rigor of verification methods, like needing formal proof for ASIL-D, the strictness of reviews, even the qualifications of the personnel involved. It's about ensuring every single part of the safety-critical chain meets the highest required standard.
Okay, what about the hardware and the overall structure?
That falls under assumptions about the technical architecture. This isn't just about general software structure. It presumes a certain underlying software and hardware architecture, which must be clearly defined and agreed upon up front. For example, it might assume the use of a specific real-time operating system, RTOS, a particular microcontroller family with known behaviors, or a defined memory model. This early explicit definition is critical because the specific safety mechanisms, resource management strategies like memory allocation, timing characteristics, and overall integrity of the software are tightly coupled with and often constrained by the underlying technical environment.
So you can't just drop this process onto any old chip or OS.
Not without careful consideration and validation. Any significant deviation from these architectural assumptions during development could invalidate the safety arguments built into the process and necessitate extensive re-verification. It requires a compatible and well-understood foundation.
And change. Software always changes. How does the process handle that?
Through assumptions about change management. This highlights another absolutely fundamental prerequisite: the necessity of a robust system for managing changes to requirements, design, and code. In safety-critical software, even a seemingly minor change like adjusting a calibration value slightly or fixing a seemingly trivial bug can have far-reaching, unintended, and potentially catastrophic consequences if not handled with extreme care.
The ripple effect.
Exactly. A prerequisite for this process is therefore a mature change management system. That includes strict version control, thorough impact analysis before any change is implemented, and comprehensive traceability to ensure that all affected artifacts requirements, design, code, tests, proofs, are systematically identified, updated, and rigorously re-verified. It's about controlling the entropy inherent in software development, especially when safety is paramount. Uncontrolled change is the enemy of safety.
What about how different software pieces talk to each other?
That's covered by assumptions about software interface specifications. This underscores the critical need for clearly defined interfaces between software components. Imagine two units needing to communicate. If Unit A expects data in a specific format, maybe an integer representing degrees Celsius, and Unit B provides it in a subtly different way, like Fahrenheit, or maybe as a floating point number.
Disaster waiting to happen.
Right. That mismatch can lead to catastrophic integration failures, even if both units are individually perfect. The process assumes that all software interfaces, how components interact, exchange data, and control each other, are precisely specified, unambiguously documented, and rigorously adhered to by all interacting components. This ensures seamless, predictable, and safe data exchange and control flow across the entire system, preventing those nasty integration surprises that can hide elusive, dangerous bugs.
Okay, and then the core technology itself, Ada and Spark.
Absolutely central. This is the SPARK process binding and the strict adherence to SPARK guidelines. This is where the chosen technology, SPARK, is formally integrated and leveraged. We've discussed why SPARK is particularly suited for safety-critical systems, strong typing, built-in concurrency features for managing parallel tasks safely, exceptional support for formal verification. The process explicitly states that adhering to specific, often very detailed guidelines for effectively using these languages is not optional. It's a non-negotiable prerequisite.
So not just using Ada Spark, but using it the right way, according to this process.
Precisely. Leveraging its inherent safety features, actively avoiding language constructs known to be problematic or hard to verify, and following coding conventions that facilitate provability, simplify review, and prevent common pitfalls. It's about maximizing the safety benefits that the language was designed to provide.
And finally, bringing it all together. Integration.
Yes, and importantly, integration verification isn't just a later step in the development lifecycle. It's defined as a fundamental prerequisite that must be considered and planned from the very outset. This means that the capability and the detailed plan to verify the integration of units, ensuring that individually verified components work together correctly and safely, must be built into the project strategy from day one.
So you don't wait until the end and hope it all works.
Definitely not. The integration strategy, including how interfaces will be verified, how shared resources, like memory or hardware peripherals, will be managed without conflict, and how timing aspects across components will be validated, must be defined early. It recognizes that system-level properties often emerge from the complex interaction of components and need their own dedicated verification strategy. It's a proactive approach to preventing system-level failures, not a reactive afterthought.
Okay, we've built the foundational understanding. We've established the critical prerequisites. Now, having laid that groundwork, we're ready to trace the actual step-by-step journey a piece of safety-critical software takes through the NVIDIA SPARK process. Section 6 of the documentation meticulously outlines this core workflow. It feels like peeling back the layers to see the meticulous craftsmanship involved, guiding us through what seems like a perfectly choreographed dance, from the initial concept of a software unit all the way through to its rigorously validated integration within the larger system. Walk us through this fascinating path.
This is indeed the heart of the process, host. And each step is carefully designed to build layers of verifiable assurance, systematically proving safety as the software evolves from an idea to working code. The absolute first and foundational element that underpins this entire workflow, mentioned right at the start of this section, is the traceability model. Now, this isn't just bureaucratic overhead ticking boxes. It's absolutely paramount in safety-critical development.
We keep hearing that word, traceability. Why is it so central?
Because a robust traceability model creates a verifiable, unbroken link between every single requirement, every design decision, every line of code, and every single verification activity. It's the mechanism through which you prove compliance with ISO 26262 to an auditor or regulator. For example, if a high-level safety requirement states that the braking system must activate within, say, 100 milliseconds, the traceability model allows you to follow that requirement all the way down, from its initial high-level spec through the detailed design of the relevant software units to the implementation of the specific lines of code that control the brakes.
And then to the tests or proofs showing it meets the deadline.
Exactly. The specific tests or formal proofs that rigorously confirm it consistently meets that 100-millisecond deadline under all specified conditions. It ensures that no requirement is overlooked or misinterpreted, no piece of code goes unverified, and critically, any change made at any point can be fully analyzed for its impact across the entire system. It's the ultimate audit trail and safety net.
Okay, so traceability is the thread running through everything. What's the first step for a specific piece of software, a unit?
The process moves to unit requirements in ADS files. This is where the detailed requirements for each individual software unit are precisely captured. The specific mention of ADS files, ADA specification files, is critical here. It implies a highly structured, standardized, and even machine-readable way of documenting these requirements.
Not just writing them in a Word document somewhere.
Right. In the ADA language, an ADS file defines the public interface of a software unit, its inputs, its outputs, its preconditions, what must be true before calling it, postconditions, what will be true after calling it, and its overall functional and non-functional behaviors, all without revealing its internal implementation. This structured approach helps ensure absolute clarity, dramatically reduces the ambiguity that can plague natural language requirements, and importantly, makes the requirements amenable to automated analysis and formal verification later in the process. It's about making sure everyone agrees on what a unit should do, precisely, before anyone starts thinking about how it will do it.
Once you know what it needs to do, then comes the how.
Exactly. Following the precise definition of requirements, we enter the unit design phase. This involves meticulously planning how each individual software unit will fulfill its specified requirements. This is far more than just drawing a few architecture diagrams. It's a phase that emphasizes incredible precision and foresight. Designers must carefully consider the unit's internal logic, its algorithms, its error handling mechanisms, its resource consumption, like memory footprint and CPU cycles.
How it talks to other units.
Yes, how it will interact with other units, and, critically, how its properties can be formally verified later. What specific design artifacts are created here? We're talking detailed architectural diagrams, precise interface control documents, state machine diagrams if applicable, data flow diagrams. The design decisions made at this stage directly impact the ease of the subsequent implementation, the efficiency of verification, and most crucially, the ultimate provability of the unit's correctness. A well-designed unit is inherently easier to prove safe.
And then finally the coding begins.
Then comes unit implementation, the actual coding phase. And here, the choice of ADA SPARK fundamentally influences the entire step. ADA, with its emphasis on strong typing, explicit exception handling, and robust concurrency features, inherently encourages safer coding practices. It makes it harder to write certain common categories of bugs that slip through easily in other languages. Spark, as a formally verifiable subset of ADA, elevates this further. It allows developers to write code that can be mathematically proven to be free from entire classes of runtime errors.
Like division by zero, null pointers, buffer overflows.
Exactly, those nasty surprises, proving their absence. This means the implementation process is a rigorous exercise in creating provably correct code, rather than just code that seems to work after some testing. Developers aren't just writing code, they're constructing mathematical artifacts that can be formally reasoned about using tools like GNIT-Prove.
So the code is written, but it's not done yet. Verification is next.
Absolutely. Unit verification is a profoundly crucial validation step. At this stage, individual software units are not just tested in the traditional sense. They are rigorously checked to ensure they meet every single one of their specified requirements and exhibit no unintended or dangerous behaviors. This phase goes far beyond traditional dynamic testing, just running the code with some inputs. It extensively involves static analysis, where sophisticated tools analyze the code without actually executing it.
Looking for potential problems in the source code itself.
Right. Identifying potential issues like coding standard violations, uninitialized variables, potential security vulnerabilities, dead code. And, most powerfully, it employs formal proof, where mathematical techniques are used to demonstrably prove that the code satisfies its properties, for example, proving that a specific function will always produce a result within a certain defined range, or that a critical safety invariant, like the brakes are never applied while accelerating, will never be violated. This multifaceted, highly rigorous approach to unit verification ensures an exceptionally high degree of confidence in the correctness and safety of each building block before it's integrated.
Okay, so each brick is proven solid. Then you build the wall.
That's the analogy, yes. Finally, we arrive at integration verification. This is the crucial step where all the individually verified units are combined, and the integrated software system is tested and analyzed to ensure that all components function correctly and safely as a holistic system. This phase specifically addresses the complex interactions and interfaces between units. It's where emergent properties of the system, things that might not be apparent at the unit level, are verified.
What kind of challenges pop up here specifically?
Unique challenges here include verifying complex communication protocols between units, ensuring safe access to shared resources like memory or hardware timers without conflicts or race conditions, and validating precise timing behaviors that only manifest when units operate together in a live environment. It's where the system's overall safety functions, like the complete emergency braking sequence involving sensors, logic, and actuators, are validated, ensuring that the whole is not just a sum of its individually correct parts, but an entirely correct, safe, and coherent system. This is the stage where the orchestra plays together, and you ensure it's in perfect harmony and tempo, delivering the intended piece safely.
That makes perfect sense. It's a journey where each step meticulously builds upon the last. But what's fascinating here, and you've touched on it, is that it's not just about writing code in AdaSpark. It's about precisely configuring and using the right tools to prove its safety. The NVIDIA SPARK Process documentation goes into, well, almost painful detail about the specific tools and verification methods, particularly in sections 7, 8, and 9. It's clear that even the smallest configuration setting or switch in a compiler or an analysis tool can have a profound, maybe even dangerous impact on the integrity of the safety case. It really highlights this artisan-like approach, doesn't it? Where the mastery extends not just to the code, but to the very environment that builds and certifies it.
That's an excellent way to put it, host. The tools are absolutely as much an integral part of the safety argument as the code itself. They are the highly calibrated instruments that allow engineers to measure, analyze, and ultimately prove the safety of the software. Consider the requirements concerning tool switches. Think of every software tool, like a compiler or an analysis program, as having this vast control panel covered in dozens, sometimes hundreds, of tiny switches and dials.
Yeah, compiler options can be overwhelming.
Exactly. Each of these switches changes how the tool behaves. Maybe it dictates how aggressively it optimizes code, or how deeply it looks for specific kinds of errors, or whether it ignores certain categories of warnings. In safety-critical development, controlling these tool switches isn't just good practice. It's absolutely critical, non-negotiable.
Why such strict control?
Because a single, seemingly minor configuration change could subtly alter how your code is interpreted, optimized, or analyzed. A compiler warning that's suppressed might hide a potential bug that only manifests under very rare conditions. A particular optimization switch could subtly change the timing or behavior of the compiled code in an unforeseen way. For formal verification, the specific switches used with a tool like GNAT-Prove define the underlying assumptions it makes about the code or the depth and scope of its analysis. If these switches aren't precisely controlled and documented, the validity of the formal proof itself could be undermined.
So the proof might not actually apply to the code that runs on the car.
Potentially, yes. So the NVIDIA SPARK process meticulously dictates every single setting for tools like the compiler, like GNAT, GNAT-Prove for formal verification, and GNAT-Check for coding standards. It demands absolute consistency, trustworthiness, and repeatability in the entire build and verification process. This eliminates a vast source of potential errors that could subtly creep in and undermine the entire safety argument. It's about leaving nothing to chance, right down to the command line arguments for the tools.
Okay, very controlled tooling. What about checklists?
Then we have the software unit verification checklists. The documentation outlines formal, detailed checklists for verifying software unit requirements and separately for software unit design and implementation. This indicates a deeply structured, repeatable process that transcends individual developer habits or memory. It means that every single unit, regardless of which engineer developed it, goes through the exact same rigorous set of verification steps. No shortcuts.
Standardizing the verification effort.
Precisely. These checklists are exhaustive. They ensure that nothing is missed, no corner is cut, and that all necessary artifacts and proofs are consistently generated, documented, and reviewed. It's a key part of ensuring quality, consistency, and compliance at scale, especially crucial in large, complex projects where many teams might be contributing. It's a literal guarantee that every stone is turned in the quest for safety.
All right, let's get into the specific tools mentioned in Section 9, the software tool usage analysis. Can you walk us through some of the key players?
Sure. This section dives into the specific suite of tools that are absolutely fundamental to this process. These aren't just generic tools off the shelf. They are a highly integrated ecosystem, mostly from Addacor's GNAT Pro Suite, designed to work together to meet the stringent demands of ISO 26262. First, GPR Build. It's essentially the project builder for AdaSpark. It acts as the orchestrator of the entire build process, managing the compilation of source code, linking various libraries, handling dependencies, and generating the final executables.
Kind of like Make or CMake, but specifically for CNET.
Exactly. It uses those GNet project files, GPR files we mentioned earlier, to understand the project structure and dependencies, ensuring that everything is built correctly and efficiently according to the specified controlled configuration. It's the core engine that turns your source code into executable software. Then, GNAT Prove. This is truly central, the star of the show for formal verification. It's a static analysis tool, but it goes way beyond typical static analysis. It uses mathematical logic and formal methods to prove properties about the code before it's even run.
The mathematical proof part?
Right. Its primary purpose is to mathematically prove the absence of certain critical runtime errors, division by zero, integer overflow or wraparound, array indexing errors, accessing memory outside array bounds, null pointer dereferences, things like that. Imagine a mathematical proof in geometry. GNAT Prove does something similar for your AdaSpark code, proving theorems about its behavior. This offers a level of assurance that traditional testing simply cannot provide. For high ASL systems, this kind of mathematical certainty is often a non-negotiable requirement.
Okay. What about NatStack?
NatStack is a specialized tool that analyzes stack usage. In embedded safety-critical systems, memory resources are often extremely limited, and the call stack is a finite resource. Precise stack analysis is vital to prevent stack overflow.
Where the program runs out of stack memory and crashes.
Exactly. A stack overflow occurs when a program tries to use more memory on the call stack than is available, leading to unpredictable behavior, security vulnerabilities, or catastrophic system crashes. NatStack helps ensure that the software will not exceed its allocated stack memory under any possible execution path or operational scenario, a common and dangerous pitfall in real-time systems.
And GNAT Stub. Sounds like it helps with testing.
It does. NetSub is a very useful tool for creating stubs, which are simplified placeholder implementations of functions or procedures that a unit under test might call. This is crucial for isolated unit testing. It allows developers to test a single software unit independently without needing to compile or link the entire complex system.
So you can pretend the rest of the system is there.
Essentially, yes. For instance, if your unit relies on a sensor input function, GNAT-stub can create a fake version of that function that returns predefined test values. This allows you to thoroughly test your unit in isolation before full system integration. It makes the unit verification phase much more efficient and focused.
Then there's GNAT Check and GNAT TKP. What's their role?
These tools are focused squarely on code quality and adherence to coding standards. GNAT Check enforces coding standards, like MISRA CC++ or custom ADA standards, and detects potential issues like style violations, unused variables, overly complex code, or deviations from best practices defined in the project guidelines. GNOTP, often standing for known properties or integrating checks based on static analysis findings, is similar, checking for a broader range of code quality issues and potential bugs based on known problematic patterns.
Why are coding standards so important for safety? Isn't it just about making code look neat?
Oh, much more than that. Enforcing standards promotes consistency, dramatically improves readability, which aids review, reduces cognitive load for developers trying to understand the code, and significantly lowers the likelihood of introducing common errors that might be difficult to spot manually or with less sophisticated analysis. They standardize the way code is written to enhance its overall clarity, maintainability, provability, and ultimately its safety.
Makes sense. How about GNet coverage?
GNAT coverage measures code coverage during testing. It provides a quantitative metric of how much of your source code has actually been executed by your test suite. It can show different levels of coverage: simple line coverage, statement coverage, decision coverage, checking if both true and false branches of an if statement were taken, and even modified condition decision coverage, MCDC.
MCDC sounds complex.
It is. MCDC is a very stringent level, often required for the highest ASAL levels, like ASAL C and D. It ensures that each condition within a decision can independently affect the outcome of that decision.
And why is high code coverage essential?
Because it provides confidence that a significant portion of the code's logic paths have actually been exercised by your tests. Low coverage means large parts of your code are untested, potentially hiding bugs or unhandled scenarios that might only surface in the field. High coverage helps identify gaps in your test suite, ensuring your verification efforts are as comprehensive as possible.
And lastly, code peer. How does that fit in with a GNet proof?
CodePeer is another powerful static analysis tool, but it complements JNAPprove rather than duplicating it. While JNAPprove focuses intensely on mathematically proving the absence of specific runtime errors based on formal specifications, contracts, CodePeer uses different, often more heuristic techniques to find a broader range of potential issues across the entire code base. This includes more complex semantic errors, potential concurrency issues like race conditions or deadlocks, which can be very hard to find with testing, and even potential security vulnerabilities. Think of CodePeer as an incredibly intelligent automated code reviewer that examines the code from multiple angles. It provides additional layers of deep analysis and essentially gives you a valuable second opinion on your code's quality and safety, identifying subtle issues that might slip past other tools or even manual review. The rigorous use of this specific suite of tools and their precise configuration down to the smallest switch isn't just a recommendation in this process, it's integral to meeting the safety standard. These tools are designed to work together, forming a comprehensive, layered verification ecosystem that systematically supports the extraordinary demands of ISO 262622. It's truly a master craftsman's toolkit, each tool serving a specific critical purpose improving safety.
That's an incredible deep dive into the precision required just at the tooling level. It really speaks volumes about the rigor involved here. Now, this next part, what the documentation labels as sections 10 and 11, feels like where the rubber truly meets the road. This is the so what moment, right? For engineers, for regulators, for anyone who needs to be absolutely provably sure this software is safe, this is how this meticulously defined process actually helps achieve compliance with ISO 26262, the ultimate benchmark for functional safety in the automotive world. It's about making that direct, undeniable, and auditable link between every single process step we've discussed and the requirements of that demanding international safety standard. How does this document achieve that critical connection?
You've hit on something vital, host. The traceability of this process, first to the assumptions made by the key verification tool JNAPprove, and then directly to the specific clauses of ISO 26262, is the absolute core of its credibility and its value proposition. Without this explicit mapping, the process would simply be a well-defined internal methodology. With it, it becomes a certifiable framework. First, let's unpack traceability to JNAPprove assumptions, Section 10. Why is understanding the assumptions made by a formal verification tool like JNAPprove so profoundly critical?
Because the proof is only valid if the assumptions hold true.
Exactly. Formal verification, while incredibly powerful and providing mathematical certainty, operates within a very precise logical framework. That framework relies on certain fundamental assumptions about the code, its environment, and even the compiler itself. If those assumptions are violated in the real world, for instance, if the actual hardware behaves slightly differently than assumed, or if data gets corrupted by cosmic rays in a way the proof didn't anticipate, or the compiler introduces a bug, then the mathematical proof, however sound in theory, might no longer hold true in practice.
The guarantee evaporates.
Right. The documentation is remarkably transparent about this, detailing specific categories of assumptions JNAPprove makes. There's shorthand and terminology used by JNAPprove's assumptions, basically defining the precise language, logical constructs, and semantic rules that JNAPprove understands and applies during its analysis. It's like defining the axioms for a mathematical system. More importantly, it covers generally applicable assumptions. These are the universal, foundational assumptions that underpin JNAPprove's effectiveness, which apply regardless of the specific code being analyzed.
Like what, for example?
Examples might include the assumption that the underlying hardware behaves correctly as specified in its datasheet, that the compiler itself is correct and doesn't introduce bugs during translation, a major area of research itself, compiler validation, or that the runtime environment, like the OS or basic libraries, is stable and functions as expected. These are broad strokes of trust that the entire formal verification chain relies upon.
Okay, those make sense. What about mixing Spark with other code?
That's covered under assumptions for mixing Spark and non-Spark code. This is particularly fascinating and crucial in real-world large-scale systems. It's rare that an entire automotive system, especially one with legacy parts, is written solely in formally verified Spark. Often, especially when integrating third-party software components or dealing with hardware drivers written in C, formally verified Spark code needs to interface with less rigorously verified or even untrusted non-Spark code.
That sounds like a weak link waiting to happen.
It can be, if not managed carefully. This section of the documentation meticulously explains the challenges at these boundaries, where provably correct code meets potentially less robust code. Critically, it details the specific assumptions made to maintain safety and integrity when integrating these different levels of assurance. It addresses how safety is preserved when data flows between a component that's proven perfect and one that isn't. This often involves using strict interface contracts, adding runtime checks at the boundary to validate data, or carefully partitioning the system.
Interesting. What other GNAT-proof assumptions are highlighted?
There are assumptions for modular use of GNAT-proof. For large projects, re-verifying the entire code base from scratch for every minor change would be impractical, maybe impossible, taking days or weeks. GNAT-proof is designed to analyze code in a modular fashion, allowing for incremental verification, only reproving things affected by a change. This section details the assumptions made for this modularity to be valid. For example, it assumes that the interfaces, the ADS files, between modules are stable and correctly specified, allowing GNAT-proof to analyze a single module without needing the full source code context of the entire system, relying instead on the contracts defined in the interfaces. And finally, there are assumptions for compiling Spark with non-GAT tools. This highlights the tightly coupled nature of this process with specific tool chains, particularly Adacore's GNAT tools.
So you really should use the GNAT tools.
The process is built around them. This section implies that if you choose to deviate and use a different compiler or a different set of analysis tools, you must fully understand and meticulously account for any new assumptions introduced by that alternative toolchain, and likely revalidate large parts of the safety case. It makes it abundantly clear that the safety argument is not built solely on the code itself, but on the entire integrated toolchain used to build, analyze, and verify it. Any deviation requires a rigorous reevaluation of the safety argument.
Okay, so that covers the tools assumptions. Now for the direct link to the safety standard itself, Section 11.
Yes, the ultimate payoff. Traceability to ISO 26262, Section 11. This section explicitly lists specific objectives, requirements, and recommendations in ISO 26262 fully met by following this process.
Wow, that's a bold claim. Fully met.
It is. It's confident and highly significant. It indicates that NVIDIA has performed a rigorous, detailed mapping of every relevant aspect of the ISO 26262 standard to specific steps, artifacts, tools, and verification activities within their Spark process. It provides a direct, auditable pathway to achieving functional safety certification for software developed using this process. Let's zoom in on a few of these reference clauses to truly grasp their general intent within the ISO 26262 standard and how the Spark process addresses them. We're mainly looking at Part 6, software level, and Part 8, supporting processes of the standard. For instance, ISO 26262 to 6.208, Clause 5, general topics for the product development at the software level. This foundational clause covers overarching aspects like defining the overall software development lifecycle, methods for managing safety mechanisms within the software, and strategies for dealing with potential software errors during development and operation.
How does the Spark process meet that?
The NVIDIA SPARK process directly addresses these by providing that highly structured, prescriptive, and verifiable lifecycle we walk through from requirements to integration. It ensures that safety considerations are embedded at every single stage, not just tacked on at the end. Then, ISO 26262 6.2018, Clause 6, specification of software safety requirements. This clause focuses intensely on how software safety requirements should be meticulously derived from higher-level system safety requirements, how they should be specified, clearly, unambiguously, verifiably, and how they should be refined down to the software unit level.
And the Spark process connection.
The NVIDIA SPARK process, through its mandatory use of unit requirements captured in ADS files, and its emphasis on concepts like implementation-free requirements, defining what, not how, directly aligns with this. It ensures that requirements are not only clear and unambiguous, but also structured in a way that's amenable to formal analysis, leaving minimal room for misinterpretation. Next, ISO 26262 is 6 Taper 12018, Clause 8, Software Unit Design and Implementation. This clause delves into the detailed requirements for designing individual software units. It covers crucial architectural design principles, defining internal module structures, interface design, and recommending or requiring strict coding guidelines.
Seems like a direct fit for the process steps.
Absolutely. The NVIDIA SPARK process, through its dedicated unit design and unit implementation phases, combined with its rigorous ADA-SPARK guidelines and those strict requirements concerning tool switches, provides an incredibly robust framework for meeting these design and implementation standards. It ensures code is not just functional, but demonstrably safe by design, using the language features and tool support effectively. Then ISO 26262-6.2018, Clause 9, Software Unit Verification. This is where the standard specifies the various methods required for verifying individual software units, emphasizing thoroughness and the need for evidence. The required methods often depend on the ASIL. The NVIDIA SPARK process excels here with its comprehensive unit verification activities. These include advanced techniques like formal proof with GenApp proof, highly recommended or required for high ASILs, exhaustive static analysis with tools like CodePeer and GATCheck, code coverage analysis with GenApp coverage, and the diligent use of those extensive verification checklists. These directly satisfy the stringent verification requirements outlined in this clause, offering an unparalleled level of confidence in each software building block. Moving to Part 8 of the standard, which covers supporting processes. ISO 26262-8.2018, Clause 6, Specification and Management of Safety Requirements. This deals with the overall management of safety requirements throughout the entire product lifecycle, from initial concept right through to decommissioning. It covers aspects like requirement allocation, change management, and consistency.
And traceability comes in here again.
It's exactly. The robust traceability model that the NVIDIA SPARK process establishes as foundational is a key enabler here. It allows for seamless and auditable management, tracking, and impact analysis of requirements across all phases of development, ensuring consistency and completeness as required by this clause. And finally, ISO 26262-8.2018, Clause 9, Verification. This is a broad, overarching clause that addresses general verification activities and principles that occur across the entire development process, not just focused on the software unit level. It includes things like verification planning, documentation, and reviewing verification results. The numerous verification steps embedded throughout the NVIDIA SPARK process, from local peer review to global peer review, from unit verification to integration verification, the use of formal methods, static analysis, testing, and the pervasive use of verification checklists, all collectively contribute to fulfilling the comprehensive and demanding verification objectives of this crucial clause. This direct, explicit mapping demonstrates the truly comprehensive nature of the NVIDIA SPARK process in achieving a specific high-stakes safety certification. It provides that clear, undeniable, and auditable trail that regulators and certification bodies can follow with confidence to confirm absolute compliance. It effectively translates the highly technical work into a language of assurance that the entire automotive industry can understand and trust.
That deep dive into the ISO 26262 traceability really pulls back the curtain, doesn't it? It shows exactly how a highly technical process translates into real-world safety assurance that regulators can accept. It's about building that provable case. Beyond the technical process itself, I found it interesting that the common document, which accompanies the main process document, provides essential background and legal frameworks. It's a subtle reminder, perhaps, that even something as intensely technical as software safety operates within broader agreements and established knowledge bases.
Indeed, the common document isn't just an appendix. It provides crucial context and transparency. Primarily, as we touched on earlier, it features the GNU-free documentation license, GFDL v1.3, for the NVIDIA SPARK process document itself. And again, this isn't just legal formality or small print. It's significant because it dictates precisely how this specific document can be copied, modified, and shared.
Reinforcing that openness idea.
Exactly. For a document outlining such a critical safety process, the choice of a free documentation license like GFDL implies a tangible commitment to transparency. It allows others within the industry, maybe competitors, researchers, academics, other safety-critical developers, to review, understand, and even adapt the process for their own needs, potentially fostering collaboration and wider adoption of best practices in safety-critical domains. In an industry where collective safety depends heavily on shared knowledge and universally verifiable methods, such transparency is highly valued. It could accelerate the overall rate of innovation and safety improvements across the board. It's quite a progressive stance for a document of this nature.
And what about the bibliography also mentioned in the common document?
Yes, the bibliography section. Though it might seem like just a list of references, it profoundly underscores the intellectual and scientific foundation of the NVIDIA SPARK process. It shows this wasn't just developed in a vacuum. By referencing existing international standards like ISO 26262 itself, obviously, seminal academic research papers on formal methods, or ADA, industry best practices documents, and other relevant literature, the bibliography demonstrates that the methodology is built upon a robust body of established knowledge and validated practices. Fields like software engineering, formal methods, programming language design, and functional safety all contribute. It lends immense credibility and ensures the process is grounded in a broader, peer-reviewed body of expertise, rather than being some purely proprietary, unvalidated approach concocted internally.
So it shows they've done their homework and are building on established science and engineering.
Precisely. It shows that this isn't just one company's idea of safety. It's presented as a synthesis of the best available knowledge, rigorously applied to the specific context of ADASPARK for ISO 26262 compliance. Tag outro.
Wow, what a journey through the intricacies of software safety. We've peeled back so many layers today, haven't we? From the precise, almost mathematical definitions in its terminology, to the incredibly specific, artisan-like control over tools like GeneProve and CodePeer, and finally, to that direct, auditable traceability to international safety standards like ISO 26262. It's abundantly clear that achieving this monumental level of software safety is absolutely no accident.
Not at all. It's deliberate engineering.
It's the direct result of a powerful combination. A provable programming language like ADASPARK, integrated with cutting-edge formal methods, all meticulously orchestrated within an incredibly strict, verifiable process adherence. This isn't just about writing good code. It's about striving for and often achieving provably correct code in the most critical domains.
Yeah, and if we connect this to the bigger picture, this deep dive into the NVIDIA SPARK process really shows us that safety in complex, high-stakes software isn't achieved by chance or by simply writing good enough code and, hoping for the best with lots of testing. It is the product of an exhaustive, systematic, and mathematically verifiable process. It leverages the power of formal methods and exercises strict control over every single aspect of the tools, the workflow, the requirements, and the people involved. It's about designing for safety from the very first thought, building it in meticulously at every single step, and then rigorously proving that safety every inch of the way.
It really changes how you think about the software running things around us.
It does. And this raises an incredibly important question for you, our listener, to maybe ponder. As technology becomes ever more pervasive and deeply embedded in our daily lives, particularly in truly autonomous systems like self-driving cars or advanced aerospace controls, or even critical medical devices controlling life support, what level of verifiable, undeniable assurance do you believe is truly necessary for the software that controls them? Where do we draw the line?
That's a deep question to end on.
It is. But it's a profound reminder, I think, that behind every complex safety-critical system operating silently in the background, there's likely a deeply structured, meticulously rigorous process, perhaps very much like the one we've explored today, working tirelessly to ensure our safety and maintain our trust.